Welcome to Control System Laboratory experiment number 11. According to your syllabus, your experiments are to study the effects of open loop poles and zeros on root locus contour, and B is to estimate the effect of the open loop gain on the transient response of closed loop system using root locus, and C the comparative study of Bode, Nyquist and root locus with respect to stability. So in this video, I'll be talking about these three uh, programs and we'll see the outputs. Now we'll go to if you have your uh, laboratory manuals with you, you can go to this experiment page and you're going to go to the experiment 11A. Okay, so the aim is to draw the root loci for a given transfer function to verify the breakaway point and imaginary axis crossover point by using Matlab. Okay, now the function you'll be given, you are supposed to find out the theoretical answers by hand calculation and match it with the Matlab output. Okay, so for the given transfer, you are given a particular transfer function, and you compute the breakaway point and imaginary axis crossover point. Okay, so use that formula of breakaway point and imaginary axis crossover point at which it crosses the imaginary axis of the transfer function in the root locus plot. Okay, and then you verify by the simulation. This is your work. So this is the program that you need to write in Matlab editor. Now here the GS, if you see the first line of the program, it has this percentage sign. That means this line is actually a comment. It is not a program line. This is not a command or any program related line. This is just a comment. So the comment says that this program here we are using GS in terms of k divided by s into s plus 2 into s square plus 6s plus 25. So it has this open loop transfer function GS has a pole at origin, has a pole at -2, and has imaginary and has poles on the roots of s square plus 6s plus 25. So you find out the poles of this GS. Okay, then our program starts. So we start with the clear, then the CLC clears all the previous previous Matlab variables. Okay, and CLC clears the command window screen. Then we use this command. We have used this command previously, which says that s, we are going to use this variable s. This s is a Matlab variable, so we are using this command. Okay, then here we are writing the Matlab. We are forming this g function. G is given by 1 by the entire thing. Remember, you are not using the value k, because k is to be determined, because k is to be varied. So you are going to use this g inside this root locus, or you have this r locus command. R locus is nothing but it finds the root locus of the g. Okay, so we are not using the k because this inbuilt function will introduce k here and will increase k from 0 to infinity. Okay, and it will plot. So we do not require to write the value of k, only write the part without the k. Okay, and then you write grid on, and nothing but you'll have vertical and horizontal lines. Okay, so this is the first experiment. Let us go to the MATLAB program. In the MATLAB program, this is the program that is written same as what has been written here. Okay, so you are going to run it. Remember to save the program, save the file in the editor. Okay, and then you run the program. Okay, now you can see this is the root locus plot. You can maximize this figure, so you can see this one pole is at the origin. You can see the origin here. One pole is at -2, so you compare this to the one pole is at the origin, one pole is at the -2. The other poles are on the imaginary axis, are on the imaginary axis. You can see these two are the poles. So here this is the breakaway point. Okay, so in order to find that, see if you click it here, you can get the value. So here you can see the gain is 20.2 at breakaway. Okay, then the gain is around 187 when it crosses the uh, imaginary axis. You can click it and you get the value. So these values are obtained. So these values are obtained from this root locus, and you are going to compare this with your calculated values. Okay, so this is the end of the first experiment of the experiment number 11. The next experiment is to estimate the effect of open loop gain on the transient response of the closed loop system by a root locus. So you have an open loop gain, that is K. Okay, now you have to it is to estimate the effect, like what is the value of K to make the closed loop system the transient response of the to affect the transient response of the closed loop system. So in order to do that, this is the program. The program is very similar to the previous program, where you have the CLC command which clears the screen of the command window. Clear all command is it removes all the previous variables that are stored in the MATLAB MATLAB program. Now we are using this GS as this value K by S into S square plus S plus 0.6. Now here we are adding poles and zeros at S equal to 0.2 and S equal to minus 0.1 to the above transfer function. We declare in the next line, we declare S to be a Laplace variable by writing this command. This command is very common in all the your control system classes. Okay, so and then we write the G. We write the transfer function G, and since we have introduced poles and zeros, that is being reflected here. So you can see there is a 0 of S equal to minus 0.1. So you have G is equal to S plus 0.1 here, and we have a pole at S equal to 0.2. So you have seen that S equal to minus 0.2 is multiplied in the denominator. Then we apply this root locus of G and write grid on. Writing this root locus of G, uh, the MATLAB finds out the root locus plot, and writing this grid on, it creates the grid so that it becomes easier for us to find out the values. Okay, so let us move on to the MATLAB program and see the root locus plot. So here is the MATLAB program. The program is exactly same as there in the in your manual. Okay, so just type in the values, make sure you understand how this program works, and then you run it. Okay, after running it, you will get the root locus plot. So this is the root locus plot. You can see these are the two poles, s equal to 0, s equal to, this is point 1, or sorry, point s equal to point pole is s equal to point 2. Okay, so s equal to point 2 is here. This is the s equal to point 2. This is a breakaway point, and then with the increase of k, this zone, and this zone are the stable zone, and beyond that, so the k is, so for a for k equal to, so if you click it here, you'll get the point. So for gain of 0.344 and a gain of 0.158, so between these two gains, that is, if the gain is between these two points, the k becomes stable. Okay, beyond that, k becomes unstable. Now what about these you can see the plot, these are the two poles. Now these two poles come join here, break away, and one goes to this 0, the other goes to 0 at the left hand side, infinity. So these are not these locuses are not important, but the locus that goes outside this right hand side, outside to the right hand side of this uh, S plane, that is important. Okay, so this is the end of the experiment number 2. Okay, now coming to the third experiment of experiment 11. Okay, this experiment is to compare and study the Bode, Nyquist and root locus plot with respect to stability. So in the Matlab program, we are going to write the value of GSHS as k into s plus 3 divided by s into s plus 2. Okay, so the same procedure as previously. Now here we have written the program in a different style. You can use you can use the other approach as well, using that declaring s as a Laplace variable. If you do not want to use that, you can, there is a one other way, is to declare the numerator and the denominator as two matrices. So you are using this variable num as the, for the numerator, as a matrix of the of column 1 and 3. That means this is 1 into s to the power of 1 and 3 into s to the power of s to the power of 0. That is not, this numerator is equal to bracket 1 space 3. It means it denotes s plus 3. Okay, and the denominator given in terms of 1 2 1 space 2 space 0 is nothing but, it is 1 into s square plus 2 into s to the power of 1 plus 0 into the s to the power of 0. It is nothing but s square plus 2s. It denotes s square plus 2s. Okay, then we are using this num and den, num and den variable. We can find that you can create the transfer function using this tf command. The tf command here takes num comma den variable. This num variable has 1 3 as matrix, and the den variable has 1 2 0 as a matrix. Okay, now this t is created as a transfer function. you can find the root locus as root locus of num comma den. If you see, the objective of this experiment is to compare Bode, Nyquist and root locus. So we are first finding out the root locus and typing in the grid on, so that you can find you can have the grids on the root locus plot. The next new command you are learning here is the pause. Pause, actually what you are doing is that we are going to use both use root locus, Bode and Nyquist, all these three together. So if we do not use pause, one, that the figure window will automatically show root locus, Bode and Nyquist, and it will show the output so fast that you will only end up seeing Nyquist plot only. So if you write the pause command there, it will wait for you to click any uh, key, or you press enter, then it will show the next graph. Okay, so the next you have to type in Bode of num and den, again grid on, and again a pause to make the Matlab wait for your signal. Okay, and then you type in Nyquist and num and den, so it will give you the Nyquist plot. Okay, so this in this program we are comparing root locus, Bode and Nyquist together. So let us go to the Matlab program and see the graph. So here in the Matlab program, it is exactly the same what it is written. Okay, so we are going to run the program. Okay, so you can see this is the root locus plot. Okay, this Matlab is now waiting for me to press the enter, so that it will now show me the Bode plot. So this is the root locus plot. If I now I am pressing enter, I have pressed enter. Now it shows me the Bode plot. Okay, then again I'll press enter. Now it is showing me the Nyquist plot. Okay, so this is the end of the third experiment of experiment number 11.